This is Dr. Hester Jiskoot from the University of Lethbridge, and this is lecture 6 of geog3710. It's about compass, the magnetic field, and GPS. How to use map and compass data is really important for interpreting your GPS reading. So it's essential to understand map and compass. So your practical part will be done in your lab 1, and this lecture is more about the theoretical background of the compass and the GPS. The compass rose, also sometimes called wind rose, is essentially a figure to indicate the orientations of the 360 degrees sphere of directions. So we usually indicate the main directions, which are called cardinal directions, as north, south, east, and west. The intermediate directions, southwest, northwest, northeast, southeast, are called the intercardinal or intermediate directions. The importance of this type of directional indication is that it's an absolute or an almost absolute direction indicator. So it doesn't matter what direction you're facing, north is still north on a compass. However, there is a difference between a geographical north and a magnetic north, and that's what part of this lecture will be about. A compass needle is essentially a magnetized pointer that aligns to the Earth's magnetic field. And the Earth's magnetic field is generated by what we call the geodynamo. The Earth's layers from the inside to the outside are the core, the mantle, and the crust. And we know this because of seismology, so seismic waves reflect or have a different direction or a different speed in the different materials in each of these layers. The Earth's core is composed mostly of metals, and the inner part is solid and the outer part is liquid. And because it's liquid, it can generate movement, and that movement is just like an electrical dynamo, a core. Here you see a transect of the inner core, which is solid, and the outer core, which is liquid. And the movement, so the fluid motion of the material in the outer core, is generated and maintained by the heat from the inner core, and the chemical differentiation that's going on. So it's kind of bubbling up, as you like. But at the same time, the Earth is rotating, and because the Earth is rotating around its north-south axis, this movement is therefore actually directed into a north-south direction. So therefore, the magnetic field is like an electrical coil and goes in the North Pole region and out in the South Pole region. This magnetic field that's generated by the geodynamo extends to outside the Earth's surface, and it generates an Earth magnetic field that actually shelters us from, or protects us from, the solar wind. So the solar particles are deflected around the magnetosphere, and we actually wouldn't be alive if this wasn't there. You can actually see the activity between some of the solar particles entering the magnetosphere on days where we see northern lights or southern lights, so aurora borealis or aurora australis. The Earth spins around its geographic axis, and that's what we call the geographic North Pole and the geographic South Pole on maps and other things. But the magnetic axis is not aligned parallel to the geographic one, and the magnetic axis is not in a stationary position. So we have a wandering magnetic North Pole and a wandering magnetic South Pole. On any location on Earth, you can actually view the difference between the location of the geographic North Pole and the magnetic North Pole at one point, and you can express that as an angle relative to where you're standing. And that angle is called the declination. So the declination is the angular difference between the compass alignment with the magnetic north relative to where the actual geographic north would be. The magnetic field lines, so basically how the magnetic field aligns relative to the Earth's surface, is not parallel to the Earth's surface. So around the equator, it's almost parallel. So you hold your compass parallel to the Earth's surface, and therefore the magnetic field exerts a force on your magnetic needle, and that will nicely align with that horizontal axis. But the closer you go to the North Pole or the South Pole, the more that those magnetic field lines actually point either inside or outside the Earth. So basically it becomes a more vertically aligned, what we call inclination. So the inclination is the field line intersect angle with the Earth's surface, and it's basically parallel to the Earth's surface at the magnetic equator, but it's at 90 degrees, so like vertically in at the magnetic North Pole and vertically out at the magnetic South Pole. So that means if you have a compass there, it would point up and down, and a compass is pretty useless when it does that. So the third property of the magnetic field that varies where you are on Earth is called the intensity. And basically that's the strength of the magnetic field at a particular location. And the strength of the field at the North and the South Pole regions is maximum, and at the equator it's at the minimum. And that's because the magnetic field lines actually converge at the magnetic North Pole. So therefore, your compass needle will actually, at the North Pole, be very strongly pulled towards the Earth center, and that magnetic field is so strong that that compass is pretty useless there. You can decompose the magnetic force that is felt by your compass needle in magnetic field vectors that are the horizontal and the vertical vector. So where the north vector, the x, is aligned to the geographic north, the y is the east vector aligned to exact geographic east, and the vertical vector z is commonly indicated as going in the Earth. So if your geographic north and magnetic north are not aligned in the same location, you basically have a resultant horizontal intensity of the magnetic field vector of h. And that is the direction that your compass needle will point to. And the angle between the geographic north and that horizontal intensity vector will be your horizontal declination, d. Now, if you're close to the North Pole, the vertical vector is exerting a large force. So vectors have a direction and magnitude, right? So if at the North Pole, the vertical vector has a high magnitude, so it's actually pulling your compass needle down. So that angle relative to the horizontal that it pulls down is I, which is your magnetic inclination. So eventually in this particular picture, the magnetic force on your compass needle is in total F. So it's actually like pointing downwards and slightly between north and east. So at the location of Lethbridge in Canada, the magnetic declination is 13 degrees. And that basically means that your magnetic north is on the east side of your geographic north. And magnetic declinations are given as positive or negative. And the convention is that we give it a positive number if it's east. The magnetic inclination is 72 degrees, so that means that your needle is slightly pointing inside the Earth. So remember, at the equator it's 0, at the North Pole it's 90. But here at this location, a compass can still be reliably used as long as you actually set your magnetic declination. The magnetic field strength is also fairly strong, 55,000 nanotesla. So in this year, 2020, the magnetic declination is 13 degrees and 14 minutes. But each year that changes a little bit because, as you know, the North Pole is wandering. So it actually increases each year a little bit by about 1 degree. So you can now set your magnetic compass. If you have a declination needle, you can set it to 13 degrees east. And if you do that, then you can use your compass together with the maps to actually like point to true north. If you have a smartphone compass, then you have to always choose the geographic or the true north and not the magnetic north compass setting. You can do a nice experiment with a smartphone compass if it's a magnetic compass, and you can put it on a table, put the setting on the geographic north, and then align your smartphone exactly to true north. Then you actually go back to the settings and you don't actually move your smartphone, so it's in a fixed position on your table, and then set it to the magnetic north compass direction. And what you will see is the compass needle will have changed, and if you do this in Lethbridge, then that will have changed exactly 13 degrees and 14 minutes east. So if you're interested, here is a website link that gives you the reconstructed position of the magnetic North Pole since about 1590 to the present. And we know this from both historical observations and models. And you see in 1590 the magnetic North Pole location started in northern Arctic Canada and wandered kind of slightly further south. And then from 1904 to 2020 onwards, it's been going steadily north. And I say north, that's like towards the geographic North Pole location. So this map also indicates the magnetic declination lines. They're called the magnetic isogonic lines, and they actually change like relative to where the magnetic North Pole is. So this particular image is from 2020, and you see the red lines and the blue lines. They're the positive, the positive and the negative declinations. So Lethbridge is kind of on the top left region of this particular map, and it has a positive declination of about 13 degrees. What you see here too is the green line, so those are the transitions between the blue and the red lines, and those have a horizontal declination of 0. So actually around kind of the European region, the magnetic declination is so minimal, maybe 0 to like 1.5 degrees, that it doesn't really matter if you navigate, leisurely without actually setting your declination. But as you know, in Lethbridge, it actually makes a large difference if you don't actually set your magnetic declination. This is a world map of the magnetic field declination in 2015, where Lethbridge is indicated with a yellow star, and we can see the east declinations indicated with the red isolines and the west declinations indicated with the blue lines. So what you can see here is magnetic declination can vary obviously between 0, no declination, to almost like 80 or 90 degrees when you actually get really close to the South Pole region. So to use a map and a compass together, you first of all need to know the projection of the map. So this is an example where you have the UTM projection, and then you also have to know the magnetic declination at that particular location. After you set your magnetic declination on your compass, you can then align the compass side to the north-south UTM lines. And if you actually like put your compass dial or your compass rose on north, you then have it aligned exactly to the geographic North Pole because you've set your declination. So what you see on the right here is my compass needle. The red arrow is actually pointing to magnetic north, but because I've set my magnetic declination to about 13 degrees east, my direction of the dial of the compass rose north is aligned north-south. So each good topographic map will also have an indication in its legend what the magnetic declination is at the time that that map sheet was printed. So what you see here is a legend entry where we have two UTM zones, zone 11 and zone 12, and the relative position of the UTM grid relative to the geographic grid are given like as different relative angles between zone 11 and zone 12. But in the center of that entire map sheet, which is composed of zone 11 and zone 12 here, you have a magnetic declination at the time of the map print, which I think is 1970 or something. So the difference between your north arrow on the map and the magnetic north here is indicated as 16.30, 16 degrees and 30 minutes. The magnetic declination is also indicated here in a different unit, mils, which is milliradians, which is also an angular measure, but of a different type. And so these maps, they're printed at a certain time. The magnetic declination is indicated for that particular time. What you need to know is how much the magnetic declination changes over time when you're actually using the map. So right now, the magnetic declination on this map sheet is actually a lot less. It's about 12 instead of 16. On the left, in the blue lettering, you have a map legend where it's both the magnetic declination given at the time where the map was printed and the annual change. So you can actually see here that the annual change is decreasing by 1.4 minutes. So not degrees, but minutes. Just like bear that in mind. So at the time of the printing of this map in 1975, that's indicated with the blue kind of arrow assemblage. The true north is indicated with the star. So true north or geographic north, they're the same. And then the grid north, so this is a UTM map, zone 20. The grid north is slightly on the west side of the true north grid. Then the magnetic north is even further west, so this would be actually a negative declination. So it's 18 degrees and 18 minutes. So your compass needle is not only directed by the geodynamo, so the magnetic field of the Earth, but also by any metal objects that are around it. So if you have a compass on ships that are iron or metal, or in aircrafts or around humans like that have metal pieces either in your body or maybe as a belt buckle or your watch, they all influence the compass's immediate magnetic field, and that can actually also deviate your magnetic direction of that needle, and that deviation can actually sometimes be like 45 degrees or something. So it's a directional error that is either constant if you have a compass like in a kind of metal or iron environment that is constant, so the hull of a ship, or it can be temporary where you move away or towards something that is metal. So when you use a compass, you always have to stay away from belt buckles, knives, cell phones, and things like that. So if you want to figure out how far away you have to be from a metal fence so that it doesn't influence your compass direction, and this is also on smartphone compasses that use a magnetic compass and not a GPS compass, you basically like go and walk towards that metal fence and then like walk away from it while you're keeping your compass pointed towards the same direction, like let's say a lamppost in the distance or something. So when your magnetic needle stops moving, it's not within the field of the magnetic deviation that particular metal fence would have exerted on your needle. So of all the three variables of the magnetic field, so deviation, we just talked about, inclination and declination. Declination is the most important one for navigating with your compass and a map. So you always have to know your magnetic declination at the location at the time that you're using the map. So this slide nicely reviews what the magnetic declination is and that it changes. So over much of the world, the magnetic declination is the most important variable. But when you actually get close to the North Pole or the South Pole, the inclination becomes so large that your magnetic compass is not usable anymore, because the magnetic compass needle is either pulled down inside the Earth or pulled upwards, and you can't actually navigate with that at all. So some people have described it as the spinning of your magnetic needle, which may do this like before you're right at the North or the South Pole, or it just kind of gets stuck, and no matter what direction you're walking or sailing or whatever, it doesn't actually move. So it's useless here. So this map indicates in about the year 2000 where the magnetic North Pole is with the star, and then which zones, like the brown or the reddish zone, is where the compass is completely useless, and the yellow zone is where it's unreliable. So this doesn't just affect compasses, but it affects anything that or everything that has some kind of navigational system that is reliant on the magnetic field. So if you want to fly a UAV or a drone here or other instruments that use compasses, they're also unreliable. And some of my colleagues have lost some drones on glaciers because they didn't actually go the direction that they thought they would go into. So again, at the bottom here, you can actually see the migration or the wander of the North Pole over time if you click on that link. And with that migration or the wander, you also have these zones where the compass is useless or unreliable, changing geographically over time. So before the wide use of GPSs and electronic navigation systems that used GPSs on board of ships, ships were reliant on using the compass. And if you're sailing in a certain area where the magnetic field has too large an inclination to use it, it will actually indicate on these nautical maps that the magnetic compass is, for example, erratic or useless. So here you see an example in the Canadian North where it tells you that the magnetic compass is erratic. So I sailed the Northwest Passage on the historic ship the Tekla in 2019, and we were kind of surprised by an event where suddenly our magnetic compass was not useful anymore. So even though we used electronic maps and electronic systems to navigate in the larger scale, if you want to keep course on a ship, you often, like, it's good if you don't have anything, no ships or no land on the horizon, to actually like keep your eye on the compass to keep like steady course. So if your magnetic compass suddenly stops working and is stuck in one particular position, you can actually go really far off course. So what I have here is a link to a little video. It's about 15 minutes long video where you can see where we are on Earth, that we're actually going into this zone of the erratic compass use, what actually happened to the ship when we were there, and some explanations by me because I was sailing on that ship. So in the video link that you saw of the Tekla and the problems with magnetic compass, I was explaining that only planets that have a solid and a liquid core have magnetic fields, and I was wrong. So I just want to set myself right here. There is planetary magnetic fields that occur also in some of the gas planets. So at least what you need to have is part of the core needs to be more kind of stiffer than another part of the core, and that liquid part doesn't need to be liquid metal, so it can be a metallic hydrogen, for example. So the 4 gas planets have extremely strong magnetic fields. The Earth, relative to other planets, has a moderately strong magnetic field. Mercury has a very weak field because the faster a planet rotates, the stronger that particular geodynamo is. And Venus and Mars have like a tiny little field, but not appreciable, so you can't actually navigate on it. And our moon does not have any magnetic field because it's a complete solid rock. So how can you tell a geographic direction or a location where you're at if your compass doesn't actually work, or if you don't have a compass? Well, you can always use the sun and the time if you have a watch. So a solar compass is a little bit like a manual sundial. So on the solar compass rose, you basically have the time of day that the sun would be in a certain time. And in the center of this, you can actually place a little needle, and then the shadow of that needle will point to the particular time. So then we can actually derive from that where the geographic north and south is. If you do that at night, you can use an astro compass, and that's actually, for example, if there's 24-hour nighttime, or if you're like navigating like through the night, then obviously you don't have a sun, you can't use a solar compass. So an astro compass is useless, on the other hand, when you're in a North Polar or South Polar region where there's 24-hour daylight, because the only star that you can see is the sun, and very occasionally a couple of planets during the day. Now we can also use just an analog watch. It basically means you need to have the hands of the watch and the sun, and I'll give you more explanation in the survival lecture. So mariners and sailors used the sextant to actually measure where the stars and the sun are in terms of like distance above the horizon and distance relative to the south. So you can only use a sextant if you also have a timetable where it tells you the height of the sun above the horizon at certain points at certain latitudes that you are. So nowadays we can use a GPS, a geographic positioning system. And almost all GPSs also have a compass, but the compass is not a magnetic compass. So if you move towards a certain direction, then your GPS compass will be able to tell what your geographic direction is. So the compass only works properly when you're moving. Now, when you're in a car or on a ship, you don't have to move yourself because your vehicle is moving. But just bear this in mind, when you're standing still with the GPS, you cannot actually use it as a compass. So for the proper background of the global positioning system, I'd like you to watch these 3 videos in this particular sequence. So the first one explains like the raw basics of the GPS, and then you get used to some terms. The second one has much more background and some history of the use, and also some national kind of indications of that use. But I have to warn you, it has some sponsor ad at the end, so you can ignore that part of the video. And then the third video is the most extensive. It has a very good explanation of 3D trilateration, but it's quite annoying like animation on it, but it's still a good background. So essentially how a GPS works is it has an antenna that receives a signal from navigational satellites, and these navigational satellites, if you have 3 or 4 in the sky, you can then do like a sort of triangulation, but if you want to know the vertical, you need to do trilateration. So if you know the positions of these satellites, you know the exact time of the signal that they send, you can then calculate the distance that you are from that particular satellite. And that gives you like a location of where you're standing with your GPS. Now, the precision of your GPS is roughly determined by two factors. One is the quality of your antenna. And that makes the difference between a basic GPS that usually you have some maps on the GPS too. It's quite affordable for almost everyone. And the maximum precision that you get is your location within 3 or 4 meters. Now, an advanced GPS, as you can see in the bottom left here, has a larger antenna and can have like almost half that precision, so within 2 or 3 meters. It sometimes also has some additional factors, so you can have like a weather forecaster or even a weather instruments. You can have like an emergency beacon in-reach system in there too, and you can actually see the price is quite a bit higher. Now, scientists use scientific GPSs that are called real-time kinematic or post-processing kinematic. And what you have with that is you have one base station where the antenna, basically the base station is stationary, it's not moving. And you can either bring that to the field yourself, or you can actually rely on a base station system that almost every nation on Earth has some of these. And then when you're in the field, you actually use a GPS, again with a really good antenna, that is called a rover. So you move the rover around, and these GPS observations or like data entries, they are collected at exactly the same time. So this is to actually reduce like some of the errors that, for example, the atmospheric interference causes between the traveling signal between the navigational satellite and the position that you are. So now we can actually go up to precisions of in centimeter range. But as you can see, this scientific GPS, it's not really affordable for basic daily use of an amateur, or for geocaching, or for normal navigational use. Questions that you can answer when you use a GPS is foremost, where am I? And a GPS gives you the location, usually in degrees, latitude and longitude, where you are. So it's a geographical location, and it also gives you the elevation. So you have a choice in terms of coordinate and grid systems and units and datums. Second question you can answer is, where have I been? When you actually walk around or drive around or whatever you use to move around, you can put waypoints in. So at each location where you are, you can put that location as a waypoint. You can pin that, and then you can later return to that particular location. So you can use the GPS to navigate to that location. You don't manually have to put waypoints in. Sometimes you can put a GPS on what we say tracks, and then there's a regular recording of the path that you go with either regular time intervals or regular space intervals. A third question that you can answer is, where do I want to go and how far is it and what route to take? So you can actually use the maps and the satellite images and put waypoints in locations where you haven't been yet, but then you can still use the GPS to navigate towards that particular waypoint. And then in addition, you can always figure out how fast you're traveling and in which direction, and often also what time it is, because time is an important recording variable within the GPS system. Because if you've watched the videos by now, you know that the time at the satellite and the time at the GPS are very important. Scientists use GPSs to take scientific measurements of any type of movement, usually slow movement at the Earth's surface. So, for example, If a volcanic eruption is expected or is monitored, then sometimes the volcano itself will swell up by maybe just a couple of centimeters over a year, and that may be an indication that the magma is getting more active. But you can also put GPSs for like a year or longer on glaciers. You can measure water and snow movement. You can measure soil creep, and you basically like put an automatic GPS in a particular location and take measurements at a set time interval. So on glaciers, for example, we can do that on a daily interval, but for some kind of motions, we actually need like a 10 minutes interval, for example. So recently, we've also discovered that we can actually measure some properties in the atmosphere with those scientific high precision GPSs. So dependent on the amount of water vapor and the ionosphere changes, so again, like related to the magnetic field too, you have a delay in your signal from your GPS satellite to your GPS receiver. Or sometimes you can have a different type of waveform. And when you actually decompose that, we've been able to figure out that we can then derive what the changes in the water vapor or other atmospheric changes were. So the GPS that we're using in this lab is a free app that you can download on any type of smartphone. It's the Gaia GPS, and it actually uses not the magnetic compass field, but your GPS field. So remember, if you're using it as a compass, make sure you actually move around to indicate it. So you can move around and then stand still for a while, but if you haven't moved before that, you cannot really reliably use it as a proper compass. So this also has a number of background maps and some other data that you can use. So the rest of the information is all in the lab handout and the lab that you're doing. Thank you.